Hello, guys. Welcome to Ramta Solutions. Welcome to your grade 12 Physical Sciences Chemical Equilibrium series. Today's video is looking at Los Chatelier's principle and the temperature change. Okay, so before we proceed, we need to remind you of some few things. So when we look at effects of temperature on equilibria, we need to note a few things. We need to note endothermic reaction and exothermic reaction. So let's talk endothermic reaction. What is an endothermic reaction? Endothermic reaction is, what is this one here? Is a reaction that releases heat, isn't it? But endothermic doesn't release, rather absorbs heat. All right? Chemical reaction that absorbs heat. All right? In other words, has heat as a reactant, then has a negative, rather positive. This one has a positive enthalpy change. Okay. It has a positive enthalpy change. Okay. It is a positive enthalpy change. This is to say delta H is greater than 0. An example would be this. Which example should I think of? Okay. Generally, I will just say A VB plus heat will give us CC plus DD. I am aware that we are talking equilibrium. I'm tempted to change this forward reaction to just left-right harpoons. Is that okay? So this is an endothermic reaction. Okay? It's an endothermic reaction. So a container that houses an endothermic reaction is cool. Okay? Has a cool container. I hope this will help you. Okay. Now, let's look at exothermic reaction. I think I should have written exothermic in the following style. So with this one here, exothermic reaction, what do we say? It is a chemical reaction that, what do we say? It is a chemical reaction that releases heat. All right? Chemical reaction that releases heat. All right? And it has heat as a product. Has heat as a product. That's what it meant. It has a negative change in enthalpy. It has a negative change in enthalpy or negative enthalpy change. Let me put it like that. Has a negative enthalpy change. By that I mean delta H is less than 0. An example here, we will say generally A plus B at equilibrium, C, let's say D, and heat. Okay? Okay. C and heat. Honestly speaking, I'm not a fan of writing these guys here, but what can I say? I prefer to really use forward reaction, but it doesn't matter. Okay? It really, oh, come on, buddy. It really doesn't matter. So let me just return them. Okay. Now, let me see what else I had said. So here, the container is very hot. Okay. The container is very hot. As a hot container. Okay. has a hot container. So I need you guys to remember, this information here. Another thing that I want you to also recall is that you don't have to be given heat like this. Your reaction can also be given in the following form. I'm going to change the color. It can be, let's see, A reacting with B, product C and D. And for endothermic, we can have a comma. Do you see this? Positive. For exothermic, let's go there. For exothermic, we can say A reacting with B, reversible reaction, D, comma, delta H being negative. Okay, delta H being negative. All right. So these are the things we need. Okay, these are the things we need. So what you need to know now is this: you need to know whether the forward reaction is endothermic or exothermic. Okay, now, oops, thank you. For temperature effect, determine whether the forward is endothermic or exothermic. Determine whether the forward reaction is endothermic or exothermic. Okay. So when the value is given there, that means the endothermic is whatever the value means. Or, sorry, if the delta H is given, that means endothermic or exothermic is whatever the value means. The forward basically is whatever the delta H means, whether the forward is endothermic or exothermic. Okay, so I'll just show you what I mean. For example, you see with this example here, it means the forward reaction is exothermic and the reverse is endothermic. And this one here, it means the forward reaction is endothermic and the reverse is exothermic. So this delta H tells you what kind of reaction is forward reaction is endothermic or exothermic. Okay, remember, if delta H is positive, it means the forward is endothermic. If it's negative, it means the forward is exothermic. So just know those things. Okay, so like I said here, if the delta H is positive, it means the forward is endothermic and the reverse is exothermic. Okay, perfect. Now, we then need to proceed. Remember, the sign tells you what the forward reaction is, and the opposite, and the reverse is the opposite. Okay, so generally, for temperature change or for effect of temperature on equilibrium, for effect of temperature on equilibrium, we note the following. We note the following. I'm gonna say one. No, not one. Increasing temperature. Okay, increasing temperature favors the endothermic reaction. Okay, increasing temperature favors the endothermic reaction. Okay. Okay. It favors the endothermic reaction. Okay. So increasing temperature favors the endothermic reaction. Okay, so increasing temperature favors the endothermic reaction. Okay, favors the endothermic reaction. Why? Remember, guys, when you increase temperature, that is, you are providing heat. Your container will be hot for a moment, but recall, we are using Le Chatelier's principle. What does it say? The system will shift to counter the disturbance. So you are increasing temperature, the system will shift to decrease the temperature. Hence, decreasing temperature. Remember, lower temperature, cold conditions are endothermic conditions, isn't it? Oh, yeah. Next one. Now we're talking decreasing temperature. So, decreasing temperature favors the exothermic reaction. Right? It favors the exothermic reaction. Right? Explanation is still the same. Right? So decreasing temperature favors the exothermic reaction. Explanation is still the same. According to Le Chatelier's principle, when temperature is decreased, the system will shift to counter the disturbance by increasing temperature. Increasing temperature favors. Oh boy, what is happening? When you increase temperature, it means you are having a hot condition, hot temperatures, and that is exothermic condition. So decreasing temperature favors the exothermic reaction. You guys got it? Perfect. All right. So we are good to go. Now we're going to use an example here. In that example, we're going to use carbon dioxide gas plus hydrogen gas, a reversible reaction of water vapor and carbon monoxide gas. This reaction is endothermic. Okay, this reaction is endothermic. So I advise whenever you come across such, you look at, let me see, I'm gonna use a different color. I think red would do, but I need to lower the font size. You see the delta H here is positive. What does it mean? It means the forward is endothermic, right? It means the forward is endothermic. And what about the reverse? The reverse is exothermic. You see this? It means the reverse is exothermic, right? Now let's look at our temperature changes. How do they affect this? Now, let's look at increasing temperature. Okay, let's look at increasing temperature. We're gonna explain how the system react using Le Chatelier's principle. Okay, when the temperature of the system is increased, when the temperature of the system is increased according to Le Chatelier's principle, according to Le Chatelier's principle, what's happening? The system will act to oppose the disturbance, right? The system will act to oppose the disturbance, all right, by decreasing the temperature, isn't it? By decreasing the temperature. So, decreasing temperature, what does it favor here? You guys got it, right? Decreasing temperature, what does it favor here? Somebody's tell me what we have said. Okay, all right. So now we will have to be careful here. So this will favor the decreasing temperature. We said it favors the exothermic reaction, right? But it's fine. You don't have to state that. But what we can say here, we will say increasing temperature, okay? Increasing temperature favors, I will explain this step, favors the endothermic reaction, okay? Increasing temperature favors the endothermic reaction, okay? Favors the endothermic reaction, right? So how does it favor the endothermic reaction? This is because the system will try to decrease temperature by absorbing heat, all right? Now, here, the forward reaction, okay, here, the forward reaction is endothermic, right? The forward reaction is endothermic. So, the forward reaction is favored. So, the forward reaction is favored, isn't it? Good. Now, what does it mean about the equilibrium position? The equilibrium will shift to the right in this particular question or this example. The equilibrium will shift to the right. Now, what happens when equilibrium shift to the right? So that means the amount of products will increase, right? The amount of products. What are our products here? It was water vapor, right? It has water vapor and carbon monoxide, right? Will increase, and the amount of reactant what were the reactants here? The reactants were carbon dioxide and hydrogen gas will decrease. Okay, the amount of reactants will decrease. Okay, now let's go check the second one, which is decreasing temperature. Let's see now. Remember, decreasing temperature favors the exothermic reaction, right? Decreasing temperature. All right, we are looking at decreasing temperature, right? So what happens? Again, using Chatellier's principle, when the temperature of the system is decreased, so you guys are seeing that we are basically saying one and the same thing over and over. When the temperature of the system is decreased, comma, according to Chatellier's principle, oh boy, okay. Let me see, what do we say? How did we end it? According to Chatellier's principle, otherwise we say law Chatelier's. According to law Chatelier's principle, the system, what will it do? It will act to oppose the disturbance. The system will act to oppose the disturbance by increasing the temperature. All right? By increasing the temperature. All right? Now, that disturbance, what was it? Decreasing temperature, we have told you, favors the exothermic reaction, right? Decreasing temperature favors the exothermic reaction. Favors the exothermic reaction, right? Cool. The reverse reaction is exothermic, isn't it? Let's go back to check. Remember that example that we're having? Here is it. The reverse reaction is exothermic. All right? The reverse reaction is exothermic. All right? So, the reverse reaction is favored. So, the reverse reaction is favored. Okay, what does it mean if the reverse reaction is favored? The position of the equilibrium will be shifting to the left. So the equilibrium will shift to the left. Will shift to the left. If it shifts to the left, what's happening with amount of products? It will decrease, isn't it? The amount of products. What were our products here? It was water vapor and carbon monoxide gas. Will decrease, and amount of reactants, what are they? They were carbon dioxide and, was it hydrogen? Carbon dioxide and hydrogen. Right, yes. Carbon dioxide and hydrogen will increase. Right? Carbon dioxide and hydrogen will increase. So this is effect of temperature to the equilibrium position. Right? So using Le Chatelier's principle, this is how we answer these questions. Okay, guys? So I'm gonna see you next time. The next video will be on the equilibrium constant. Stay tuned. That one will be quite lengthy because we're going to be giving you so many wet examples. Okay? We're going to be giving you so many wet examples. All right. So this is it. We leave it here and bye bye.